So this next section of the program provides an opportunity to get a closer look into some of the systems analysis that we do in GCEP to help inform us about what are the most important attributes of new energy technologies, for example. And we have our postdocs who perform this research. And the first of them is going to be Charlie Barnhart, and he's going to be talking about energetic and material limits to electrical energy storage. And I think that the talks you just heard were a great introduction to that. So Charlie's a postdoctoral scholar at GCEP. His efforts focus on identifying technology attributes that can best reduce energy and material use as well as cost. He was a national postdoctoral fellow at NASA in 2010, and he earned his PhD in planetary geophysics at UC Santa Cruz. So welcome, Charlie.
It's been a real privilege to work at GCEP. It's been a very enriching experience. And so this afternoon I will share some of the research I've been doing on material and energy limits to electrical energy storage. And so I'm talking about very large electrical energy storage, grid scale, the so-called gigawatt day challenge. And grid scale electrical energy storage will become increasingly more important as our penetration of renewable resources increases in the electrical supply mix. Stable operation of the electrical grid is paramount. In developed nations, a power failure can mean the difference of hundreds of millions of dollars. In developing nations, stable power grids allows a soil in which manufacturing plants can take root. But this job will become increasingly challenging. It already is challenging. This is the California ISO control room. It is a military secure facility, and if you look closely, not a single person is looking at YouTube or checking their Facebook. And it's going to become more difficult with increasing renewable resources. So this is a pretty popular plot, and it's popular because it's visceral. This is my own casting of it. And I have here 30 days of wind in blue, 30 days of solar in yellow, and 30 days of power demand in red, all superimposed on each other. So the y-axis is the normalized power values for these different features, and the x-axis is time of day. And as you can see, the wind does not correlate with power demand, and solar energy is only available when the sun is shining. And so as these resources increase on the grid will need to come up with so-called grid firming services to balance out their intermittency. There are a couple technologies that exist today and that are used today. Mainly, we use hydroelectric electricity generation to firm these resources or any grid transients. And then natural gas firming is another technology used today. In the future, we may use so-called demand-side management and load balancing, and also electrical energy storage. Electrical energy storage presents an elegant solution because we're able to store energy when it's not needed and then provide it when it's actually needed. So it leads to better resource utilization, better capacity factors. All right, so how much energy storage might we need in the future? Estimates range the entire gamut. Some people say we don't need it at all. Other people say we may need 3 days. A few sophisticated studies have come out recently out of the National Renewable Energy Laboratory and from Paul Denholm in 2011 and 2012. They estimate that we may need 4 to 12 hours of storage. Now, these units aren't energy units, they're time units. And so what they mean is 4 to 12 hours of average power delivery. So this corresponds at global scale, if we take the average power demand by the entire globe, to 8.4 to 25.3 terawatt hours of energy. And so with this envelope, I can begin to navigate this question of, will there be material and energetic limits if we were to build out this much storage in some future scenario with a grid that's heavily dependent on renewable resources? The storage technologies that I included in this analysis are ones that exist today. They've been demonstrated commercially. And they also were selected based on their potential economic viability. I really wish I could include the two storage technologies I saw in the last two talks, because they somehow divined the punchline of this talk, and that they've realized what we need to focus on for grid scale energy storage. And so the technologies include 3 electrochemical batteries, 2 flow battery technologies, and 2 geologic storage technologies. All right, so beginning with material limits to energy storage. We can take a naive first step and ask how much elements that are critical to storage technologies are available to society. So how much elements are available within the lithosphere. So this plot shows on the y-axis lithospheric abundance of storage critical elements versus their annual production in tons and their price in US dollars per kilogram. As one might expect, as an element becomes more rare, less of it's produced, and the more expensive it becomes. We can take this analysis a step further by using a tool that's been developed over the last decade, the so-called energy storage potential. This is a theoretical calculation, and so it considers the theoretical energy density of an electrical chemical couple, the production of the limiting molecule or element within that couple, and this is divided by the mass fraction of that limiting element. The production value that I'll consider here is the annual production worldwide of storage critical elements. This is a busy plot, so I'll step through it slowly. On the y-axis is this energy storage potential value. For reference, here's the present day energy storage capacity. It's about 100 gigawatt hours. And the average world daily electrical demand is 50.6 terawatt hours. Here's that 4 to 12 hour storage capacity goal. And let's look at just the annual production of elements averaged over the last 6 years or so. And so this is the energy storage potential if we took all of a particular element, mined it, and delivered it and built batteries out of it. So if we took all of the lead that's mined over the course of the entire year, built batteries out of it, we'd be able to store 1 terawatt hour of energy. Right away, we can see that some elements are much more challenged than others. Some technologies are more challenged than others. We can provide a minimum, and I do mean minimum time in which we could reach this 4 to 12 hour capacity goal, because it would require all of our production going into batteries by looking at how these energy storage potential values grow over time on the x-axis. Some technologies like lithium-ion batteries and vanadium redox struggle to meet this 4 to 12 hour capacity goal. Other technologies based on abundant resources exceed this capacity goal. Production values aren't the only thing that matter. We also need to consider economically viable reserves. So economically viable reserves are not a measure of how much of a material is within the lithosphere. It's a measure of how much material is able to be extracted at profit. And so a technology like lead-acid battery that will begin to bump up against this economically reserve base will necessarily require an increase in the price of lead so that reserve base can grow. With this reserve base estimate, we can now also plot geologic storage technologies on this plot. So at the top right-hand corner are estimates for compressed air energy storage. I should mention the caveat that all compressed air energy storage systems that exist today, the 2 of them, they exist in salt dome cavities. So these will be very liberal estimates. One involves saline aquifers, the other deep gas reservoirs. And then the estimate for pumped hydro is towards the bottom of that plot. It's a simple estimate by the Energy Information Agency of 10 times present value. The take-home message from this plot, from a materials perspective, promising technologies include compressed air energy storage, sodium sulfur, and zinc bromine batteries. All right, moving to energetic limits. All right, to build a battery, energy is consumed in producing the materials, and energy is consumed in taking those materials and combining them and manufacturing a battery. This is so-called embodied energy. This plot shows the amount of embodied energy required per unit capacity, storage capacity of different technologies. In green is manufacturing energy, in blue is production energy, and in red is total energy. The one way to read this plot, using lead-acid battery, for example, it takes 321 units of energy to produce 1 unit of storage capacity. Now, this is a static, upfront energetic cost for these different technologies. There are dynamic effects that are in play when the battery is used over its lifetime. There could be energy losses due to inefficiencies, and so that's an important parameter. A battery that has a poor cycle life or low cycle life will need to be replaced more often, so these embodied energy costs will be incurred more frequently. And also, the depth of discharge of different battery technologies becomes important. If you can only shallowly discharge a battery technology, then you'll necessarily have to build a bigger battery to provide the equivalent capacity. So similar to levelized cost of electricity, we performed a levelized cost of energy analysis for these different technologies. So this, again, is in some distant future grid in which we need a tremendous amount of storage, and we'd like to maintain that storage for 30 years. This plot is similar to the materials plot, and it shows, again, on the y-axis, the energy storage capacity with that 4 to 12 hour capacity goal in red. But now on the x-axis, it's the amount of embodied energy required to provide an adequate amount of storage capacity. The different lines represent different technologies, and they're ordered in the same way they are in that legend, if the colors are hard to see. You can see right away that geologic storage technologies require an order of magnitude or less embodied energy than the electrochemical technologies. And the electrochemical technologies begin to impinge slightly on the world energy primary energy supply. So a lead-acid battery, for example, would require 1 to 3% of all of the energy provided by society for a course of 30 years or so. Promising technologies from an energetic perspective include CASE, compressed energy storage, pumped hydro storage, and lithium-ion technology if we're going to be forgiving and include an electrochemical technology. So at GCEP, we try to identify ways to improve technologies such that they can alleviate the energy and climate problems facing society. So to this end, we developed a new metric that includes several of the different parameters within storage technologies. It's called the energy stored on invested, or ESOI. And it has parallels, obviously, with the energy returned on invested. So this is the total amount of energy stored over the entire lifetime of a device divided by the amount of energy that went into building that device. Using this metric, it puts all the different technologies on a more even playing field because we do not need to use a levelization period. And we can see right away that, again, geologic storage technologies are much more favorable. I find it quite sobering to realize that a lead-acid battery only stores twice as much energy over its entire lifetime as went into building that technology. Now, obviously, it's a high-value technology. We want to start our car in the morning, but still, from an energetic perspective, it's pretty egregious. All right, so using this energy storage on investment parameter, we can do some sensitivity analysis and explore which parameters we should focus research and development on to increase the amount of, to minimize the amount of energy these technologies use. And so here we can see that efficiency varies by a factor of about 1/3. The embodied energy, or E-gate, varies by about a factor of 5 between different technologies, but cycle life varies by over 2 orders of magnitude. So clearly we can maximize this ESOI value by focusing on improving cycle life. And I was very happy to see that the last two talks, Scott Barnett's and Yishui's talk, really focused on improving cycle life. They divined my results. So in conclusion, we should focus on using earth-abundant materials, compressed air energy storage, sodium sulfur batteries, zinc bromine. These are promising technologies from a materials perspective. From an energetic perspective, again, it's the geologic storage technologies. That is, unless we can increase the cycle life of electrical chemical technologies. And so for that reason, we should focus R&D on improving cycle life, and secondarily focus it on improving or reducing the energy costs of embodied energy. And so finally, through this analysis, I don't believe that storage is limited in any real sense of the word. I think that it could easily play a dominant portion of firming the electrical power grid, but it would probably play best in concert with other grid firming resources like natural gas firming and demand-side management. Thank you for your time. I'm happy to answer any questions.
So, a question on the methodology for the embedded energy in some of these materials. Many of these are produced by getting multiple materials at the same time, and if you're mining, for example. Did you allocate that in proportion to what was recovered, or how did you treat that?
The embodied energy in the materials?
Right.
All of this, we performed a meta-analysis of different life cycle assessment studies. And so a lot of these studies have come from the national labs and from a firm in Sweden. And so we used their data and then performed the analysis and developed the energy stored on investment methodology. So I do believe they do consider different materials, and they use sophisticated software suites to determine these.
But I think his question is, if you were to allocate all the energy to mine a material to that element, right now many of these are produced as byproducts.
I see.
So if this became the dominant reason for mining, would you have to allocate a lot more energy to that?
So I'm curious about that question as well. And so I tried to look at it from a more theoretical perspective and determine how much energy goes into producing a kilogram of material. And I've looked at a few different sources that have tried to extrapolate this. And it, of course, depends on the mineralogy of the rock and whether or not it's coming from a brine or a rock. But here are some of the data plotted here. And so this is the energy storage potential normalized by the embodied energy. And from this analysis, we can see that brines are much less energy intensive than elements that are locked in minerals. And so it's a good question, and it's something I'd like to explore as well.
Okay, more questions? Oh, there's one over there.
Yeah, Scott Barnhart from Northwestern. Are you able to run your calculations on a new storage technology?
I would love to. I need the life cycle assessment data or perform it myself. And so one thing I would like to do is talk to different storage technology researchers, developers, and providers and figure out what goes into making their batteries, and so that I can use a software suite to determine how much embodied energy is involved in the creation of those technologies. But again, from that energy stored on invested equation, before I'm able to round up the embodied energy of all these myriad technologies, focusing on improving cycle life is the best way to maximize this variable, this value.
Okay, all right, one more, and then we'll move on.
In your pumped hydro storage, I would imagine that a lot of the current pumped hydro is built in ideal sort of geographical locations where you have a mountain nearby. You need 100 meters or something to get a reasonable energy density. In your cost analysis of pumped hydro, if you go to someplace like Kansas, you're going to have to pile up a lot of dirt, which raises the cost.
Right.
Is that included in any way?
No, this is not included at all. We assume, well, all pumped hydro facilities are built in ideal locations. That's why they were built there. And the life cycle assessment data is acquired from those facilities. Because they have such better energy performance, one thing that I could do is consider the energetic cost of transmission from an ideal site to a load center where it's actually needed. My suspicion is that the energy required for transmission included in this analysis would still put geologic storage ahead of electrical chemical technologies at this point.
Okay, all right, well,
Thanks.
thank you very much. Okay, so the next speaker is going to be Michael Dale, and he's going to be talking about the energy balance of the photovoltaic industry, and again, asking those questions about embodied energy and to what extent it poses a constraint on the growth of development of renewable energy technologies. Again, he's a postdoc at GCEP. He studies energy requirement for energy production technologies. He got his PhD in mechanical engineering at the University of Canterbury in New Zealand. So welcome, Mick.
Okay, hi everyone. Thanks for the introduction, Sally, and thank you very much for the opportunity to present my research. If we just go back to the title slide. So as Sally was saying yesterday, the opportunity, the solar resource is absolutely huge compared to current human consumption. But as this slide kind of illustrates, the resource is very dilute, and so we have to put out a lot of infrastructure in order to try and capture it. And so this analysis tries to get to the roots of that, like what are the costs of that? And we're going to use this net energy perspective in order to work that out. So here's just a quick outline of my talk. I'm going to give you a background for the PV industry, and then I'm going to talk of some of the energy inputs to the PV manufacturing, then talk about this dynamic net energy analysis, the method that I use to do the analysis, and talk about my results, and then give you some conclusions. Okay, so PV industry. We're often presented with slides like this of the PV industry growing rapidly, and here we've broken out the global installed capacity by each of the different technologies. This is between 2000 and 2010. And the first thing to note is that it's growing rapidly. So over that 10-year period, it averaged kind of 40% growth per year. The next thing to note is that the major player, 90% of the market, is currently crystalline silicon. And we'll explore a little bit more what implications that has. Another thing to notice is that currently around about half of PV is manufactured in China, and then it's currently mainly shipped and installed in the EU, and we'll talk a little bit about the greenhouse gas implications of that as well. So, as I said, most of the PV manufacturing is currently silicon, and in order to manufacture silicon, first we have to purify it, and it's done in places like this. It's been compared to being in the bowels of hell. Basically, you have to melt rock, melt this silicon, take it up to 2,000 degrees and hold it there while the impurities kind of settle out. And that's just the first stage in the process. Once you've got the silicon, you then have to remelt it. You then have to remelt it in order to form the crystalline structures. You then have to chop it up into these thin wafers, then apply coatings and contacts in order to form the solar cell. Then have to gather these cells together and put them together with the frame and the glass encapsulation, and then put them together into this into the system with all of the balance of system components, the support structures, the wiring, the grid connection, all of this kind of thing. Now, if we look at a breakdown of the financial costs across this production chain, we can see that a third of the cost is in this final stage in just building out the system. Once you've got the modules, you're putting them into the system, so all of the balance of system components and permitting and that kind of thing. If we look instead at the energy costs, we can see that only 13% of the energy cost is in that final stage, and over half of the cost is just getting us to the ingot itself. So, as it says there, the financial costs are not equivalent to the energy costs, and the kind of proviso of that is if we're going after financial cost reductions, we might not be reducing the energy cost of producing these things. So in a similar way to Charlie, I did a meta-analysis of life cycle assessment to look at the energy costs of producing these systems, and this is a metric called the cumulative energy demand. And the first thing to notice, so it's split out by the different PV technologies. The first thing to notice is that in general, thin film technologies are slightly less energy costly to produce. So that's going to, so at the moment we're presently installing 90% of the crystalline silicon, so this has a higher energy cost. The second thing to notice is that these assessments were done, I don't know if you can read this, but between 1990 and 2010. So this is like a 2-decade time span. And you'd hope that over that sort of time period, we're getting better at learning how to produce these cells. So in order to capture this kind of idea, we borrowed the idea of the learning curve from the financial guys. And so here we're plotting this cumulative energy demand on the vertical axis in a log plot. But this time, instead of plotting against the year, we're plotting against cumulative production. So this is kind of a metric or a proxy for experience. And what we can see is that as we're producing more of each of these panels, and we've got 4 of the different technologies here, we're actually getting better at producing these systems, and learning is actually reducing the cost of producing these systems. Okay, so I'm going to change tack slightly now and talk about dynamic net energy analysis. So here we can see the inputs in and outputs from these PV systems. So in blue, at first we have to construct the system, and then once it's constructed, it starts producing electricity, or producing this energy output, which is in yellow. And for this particular case, I'm going to assume that all of the inputs are up front. So the only energy cost is in producing the PV system. And then once it's produced, then you're just producing energy from it. And if we look at an industry composed of this, where we've got this 2-year life energy payback time. So once you produce the system, it starts producing energy, and after 2 years, you've produced enough to pay back the initial upfront cost. If we imagine an industry composed of these systems, and it's growing at 100%, in the first year, we build one system. It then starts producing energy, but we build out 2 systems, and so on and so forth. We can see that this industry is pretty quickly going into deficit. It's consuming more energy in installing these systems than is being produced in each year. Obviously, this kind of exponential growth can't continue forever. So if we take a step back, we can see that as the growth rate slows, this gross output, which is kind of asymptotically going up to this limit up here, as the growth rate slows, this net output, which is this dashed line, goes through some minimum level. And at some point, we'll cross back over, and we'll have a positive net energy production by this industry. And we call this year the break-even year. Up until that point, energy is having to be put into the system, and this is this energy subsidy. After a certain amount of time of positive net energy production, enough energy will have been produced to have paid back that energy subsidy, and we call that the payback year. Now we can recast this in a slightly different light by using this plot here. So now on this, we've got the growth rate on the vertical axis, and this is in percent per year. And we've got on the horizontal axis the cumulative energy demand, so how costly this technology is to produce. So we can see that if we've got a high energy cost, cumulative energy demand, and a high growth rate, we're going to be well into this energy deficit region. Whereas if we've got a low energy cost and a low growth rate, we're going to be well into this energy surplus region. Okay, so what happens when we apply this to the PV industry? We can see here, this is the trajectory for single crystalline silicon. We can see that between the year 2000 and 2010, we can see in the year 2000, this technology was just about at this break-even level. It was producing just about as much energy as it was consuming. Then by 2002, the installed capacity had grown, but some learning had occurred to reduce the cumulative energy demand, so they were less costly to produce. But because the growth rate had increased so much, it went further into this energy deficit region, and this continued right out to 2010. A similar pattern emerges for each of the different technologies as well. We can see that all of them, well, most of them start in or around the break-even threshold and go into this energy deficit region. That is except ribbon PV, which has kind of fallen out of favor for some reason, not quite sure why. The other thing to note is that the thin film technologies, CAD-TEL in particular, has the lowest of the cumulative energy demand, but because it's growing at such a rapid rate, around about 160% per year, or was in 2010, then it's still well within this energy deficit region. And we can combine that together to have one overall plot for the whole PV industry, and you can see that it's kind of tracking this break-even threshold, but it's always within the energy deficit region. So if we take this information and we then projected it forwards to see at what point the PV industry as a whole would break even, but we also did a sensitivity analysis across all of the different parameters. So here we can see that in green is the gross energy production, and we've got historic values plotted as these diamonds here. And we can see that, so in red we've got the net energy production, and the thick line is the mean output across all of these sensitivity runs. And then we've got 50% confidence interval and 100% confidence interval. And we can see that the PV industry broke even or will break even sometime between 2006 and 2014. Okay, so let's look at some of the conclusions. So the PV industry is now likely to be a 50%, with 50% confidence, is likely to be a net electricity producer. And will almost certainly become a net power provider by 2015. And the industry will have paid back this energy that's consumed in its early growth by 2018. So there's this kind of 3-year lag between being a net provider on an annual basis and then paying back this energy subsidy. And I talked about building panels in China and then shipping them over to the EU to offset energy there, or offset electricity there. If you think in China we're using coal energy to produce these panels, and in the EU the emissions factor is much lower. So you can kind of imagine this worst case scenario, which is what we have here, whereby we imagine if all of the modules were produced in China and then all of them were shipped over to the EU to offset electricity there. And even in that worst case scenario, the greenhouse gas emissions balance, we became started offsetting more greenhouse gas emissions than we were producing 3 years later than the electricity break-even point. Okay, so some implications from all this. As I said, not all financial cost reductions lead to reductions in embodied energy, so economic analysis should be supplemented with energy analysis. And then the next two are kind of obvious. PV systems with lower energy costs provide more net energy. These systems should also cost less money and produce lower greenhouse gas emissions. So I said that we're likely to be, or the PV industry is likely to be a net electricity producer at the moment, and it's probably consuming around about 90% of its own production. But this doesn't mean that the job is done. We can't run an energy system on, well, it's no good to us that the whole energy system will consume 90% of its own energy. And if we kind of extrapolate this out, then by 2025, at current growth rates, the PV industry would be consuming around about 2,900 terawatt hours per year. Whereas if we continue to try and drive learning down this learning curve, then by 2025 it would be around 300 terawatt hours per year, or around about 8% of gross output. So we need to keep pushing on these technology developments. And so towards this end, we think that reducing the energy costs of PV system deployment, PV system production should be an explicit goal of technology deployment. And this applies not just to PV systems, but to all technologies as well. So with that, I'd like to make my thanks to GCEP for funding this research, and thanks to all these people for giving me guidance along the way. And thank you to you for listening.
Yeah, Rob Braun, Colorado School of Mines. Thanks for that presentation. I was curious, when you do these analyses, if the quality of the energy employed is a part of it. So clearly electrical energy is higher grade versus low temperature thermal, which could then affect the analyses. So more of an exergy basis versus an energy basis. So if I have 1 million kilograms per hour of low temperature water involved in the process, it has an energy value. But it's not the same as using high-grade electrical energy.
Yeah, so most of the inputs into PV manufacturing are in the form of electricity, around about 90%. And I assumed that the 100% of the inputs were in the form of electricity. So I was kind of aware of that, yeah.
Okay, we got another one, I think, in the back. All right, another question. How about over here?
Does this take into account the The thickness of the silicon in crystalline solar cells has been decreasing at a fairly rapid rate. Does that carry through in this analysis?
So we didn't model that explicitly, but that would be part of this learning that's occurring, we would think. Yeah, yeah. That's something that we're kind of planning to look into now, like trying to dig into the reasons behind this learning and trying to tease out those factors.
Okay, another question? Yeah, how about right over there?
I'm not certain how they do it in the EU, but in the US, if the solar panels are on a roof, they don't offset any carbon because the power facilities can't anticipate the irregularity. Only if it's a utility facility, then they can plan for it. Did you calculate that into your estimates?
No, we did a very simplistic greenhouse gas emissions analysis. Yeah, we just assumed that if it was producing electricity, then it was offsetting at the average emissions factor. Yeah, it's very simplistic.
All right, one more question? Okay, how about back there, and then we'll move on to that.
So if I look at the numbers, they might look to some people that these numbers are high, like, especially when you mentioned the 90% energy consumption over the overall energy consumption. But just to put things into perspective, if you can give us an idea, have you came across other numbers of how the solar industry compares to other energy industries? Like how much would be the energy consumption to build an offshore oil rig or a wind farm or a wind turbine or something like that, to see exactly how energy intensive this industry is?
Okay, so what you find is that for wind, it's on a per capacity basis, it's kind of comparable. So they're all around about 2 kilowatt hours per watt of capacity. But you get a much higher capacity factor, so it's around about double or perhaps even 3 times as much. So on a per kilowatt hour basis, it's much lower. Does that make sense?
What about fossil
For wind.
energy?
Fossil energy, it's a little bit harder to compare, but you can think that for the energy sector as a whole, you want the consumption of the energy sector. We can kind of do a proxy measure by looking at how much money we spend on energy. And it seems to be that once that spending gets above 10% of GDP, then we start to see problems within the economy. So you can imagine that the energy sector as a whole wants to be consuming less than 10% of its total energy projection.
Okay, all right, well, thank you very much.